Okay, so welcome back, and right now we're going to talk a little bit about Hess's law, and we're going to try and relate it to the three thermodynamic terms, and that would be entropy, enthalpy, and free energy. So essentially change in entropy, change in enthalpy, or change in free energy that occurs during a chemical reaction. So Hess's law can be applied to changes in standard free energy and also changes to standard absolute entropy. Now we've seen Hess's law before, where we would be looking at more of an application to changes in enthalpy. So most common application of Hess's law in these cases is going to be a comparison of product and reactant values. So typically you're going to be given some type of a table. In this case, the table is for changes to standard entropy and changes to standard enthalpy of formation. And so a combination of these two terms will allow us to calculate for delta G. The process that we're using for changes to standard entropy and changes to standard enthalpy are pretty much the same equation. It's just what values we're drawing out of the table. And the same would be true for changes in standard free energy. So if you were given a table with change to standard free energy values, you could calculate that very much the same way. But a lot of times what ends up happening is you're going to be using an equation that's going to relate free energy to the enthalpy and entropy changes. So relating the change to free energy, standard free energy in this case, to changes in standard enthalpy and standard entropy. So as we go through this, questions asking us to determine the change to standard entropy, change to standard enthalpy, and change to standard free energy for the following reaction. And then it's also asking us, is the process spontaneous under standard conditions? So what we first need to establish is our change to standard entropy and change to standard enthalpy values. When it comes to calculating a change to standard enthalpy, which means also that I'm missing the degree symbol there, so let's make sure I get that added in. What I'm going to be using is the enthalpy of formation values. You'll know it's an enthalpy of formation because you're going to see that F there. So make sure that you have that F drawn in. Alright, this is a value that describes the enthalpy for a particular substance, not for an entire reaction. Alright, the only way that this number works for an entire reaction is if you're looking at the formation of a substance from its elements. So for example, right, negative 286 describes essentially this process, changing the elements into the compound, so the elements in their standard states into the compound. That would be a match for this. Other than that, that's the only time, that's it. That's the only type of complete reaction that will be described by this value. Otherwise, what you're calculating for is the enthalpy, standard enthalpy essentially, for the reaction. Sometimes maybe you'll get this system, or another way it might be is reaction, but that's rare. Typically they're just going to leave it as this is what is describing this entire process. Okay? So if you're reading the F, right, if you're reading a little F, that means that it's for a single substance. So with that being said, we've got to figure out how we're going to set this calculation up, how we're going to go ahead and get this worked out. And so we need to use this equation, that this value here, right, the change in enthalpy for the system, for the reaction, is going to be a difference in the total product enthalpies and the total reactant enthalpies. And so now the question might be, alright, how are we going to work this out? Well, we know that the products are what we're going to be summing first. And this summation comes from taking the coefficient times the value that we're finding in the table for the enthalpy of formation. And so we have this for, let me redo the circling there because I just totally misled everybody. So as we're doing this coefficient for the product water goes right here, and because it's water, its value, right, it's liquid water no less, let's carry out that underlining, negative 286, so the negative 286 goes in here. Then we move on and we deal with this substance, carbon dioxide, the other product. It's gaseous carbon dioxide, and we find gaseous carbon dioxide there, and so its value is negative 395. Notice that we've got the multiplications bracketed so that we deal with those processes, and then I have parentheses here to make sure that we do this addition and multiplication before I approach the subtraction. Same is going to be true on the reactant side of the equation. So over here, now we're going to deal with this 2, and there's 2 of this, right? 2 of the ethine, and its gaseous state, we've got ethine gas, and its value is 227, that goes in right there. Now, when it comes to oxygen, you'll notice that it's given in the table, but if you're ever presented with an element in its standard state, and you don't have an enthalpy of formation value for it, you can trust that it will be 0. Standard state for oxygen is gaseous oxygen. We have 5 of them, so that's why there's a 5 there, but its enthalpy of formation value is 0. And again, that value didn't need to be included on the table. It could have been left blank, and if it was, you would have known it was 0. Whereas for compounds like water, carbon dioxide, or ethine, you're going to need to be able to look that up. You wouldn't be able to figure it out just on your own. You'd have to go to some sort of table of values to be able to look it up. So, doing all the math, you should end up with a value of negative 2600. Now it comes time to go ahead and deal with, change to the standard entropy. So again, got those standard symbols missing, so let's get those in there. Make sure everything looks official. And then what you'll notice this time is that the coefficients are the same as they were last time. But now the entropy values have all been introduced. And every substance, be it an element in its standard state or a compound, is going to have an entropy change value. An absolute entropy value. And those are shown here, and those came from the table up here. You can take a look here if you need to and kind of keep scrolling, but for water it was 70, for carbon dioxide it's 214, for oxygen it's 205, and for ethine it's 201. So as we're looking at this, we would expect to have 2 times 70, 4 times 214, 2 times 201, and 5 times 205. Let's make sure that that's the way that this ended up working out. So as I was saying, 2 times 70, 4 times 214, 2 times 201, and 5 times 205. So the change to the standard entropy is negative 431 joules. And that's something else to point out, is that you're going to have your enthalpy value given in kilojoules, but your entropy value is going to be given in joules. And so that's a difference in the unit there, which means that when you go to work this problem, you're either going to have to turn joules into kilojoules or kilojoules into joules, because in order to solve this problem, the units have to match. If you don't allow that to happen, your answer is going to be incorrect. So with that being said, oftentimes the way that this problem will be finished off when you're being asked to solve for standard free energy change is you're going to use this equation right here. So you've already established the standard enthalpy value, which is negative 2600 kilojoules, which could also be reported as negative 2,600,000 joules. And then you've got your negative 431 joules over here being multiplied times 298. Why? Because this is standard conditions, so the temperature has to be standard, which means 25 degrees Celsius or 298 Kelvin. The other possibility is that you would have negative 2600 kilojoules, and then you would take that and subtract from it 298 times negative 0.431 kilojoules. So it's kind of like this weird diagonal, according to the way that I've got this set up. Where it's one or the other. But nonetheless, because the standard free energy is negative under standard conditions, the process should be spontaneous under those conditions. So I'm hoping that this was helpful to you. Please make sure that when you're dealing with any of these, be it enthalpy as we see here or entropy as shown here, that you do follow the equation and you take your products and subtract away your reactants. You'll remember that when I first went to solve the problem, I used the coefficient for ethine over here. Thankfully, it worked out because it was the same coefficient as for water. But if I had used the value for ethine here in place of the value for water, my math would have been incorrect in trying to solve for the change to standard enthalpy. And I'm adding those degree symbols there to indicate that throughout the calculation it should be standard enthalpy. Down here you have a bit more involved version of the equation being shown, where n is that coefficient from the balanced equation, so it's like the number of moles. And then it's going to multiply times the products. That's why we had, it's going to multiply times that absolute entropy value from the table. So coefficient for the water was 2, and then 70 was the value. Then there were 4 CO2s times its standard entropy value of 214. Then over here we had our ethine, 2 of those times its standard entropy, or absolute entropy rather, and then we've got 5 coming from the oxygen times its absolute entropy. So take a look through. I think the setup is relatively straightforward. The main thing, obviously you need to establish before you can get going, is you got to have a good balanced equation. Once you got a good balanced equation, then what you can do is start looking up the values that you need. You can find them in the appendix of your textbook if you need to help you get through the problems, especially if a table is not given to you. But on the AP test or a quiz or something like that, if I or the College Board wants you to calculate for these types of things, then they're going to give you a table of information that you can utilize. So be clear on what it is that you're solving for, because another possibility. Okay, so another version of this problem that they can throw at you is not so much calculating for the enthalpy of a reaction indicated with this symbol, but rather they could potentially ask you to solve for the enthalpy of formation for an individual substance, like CO2. So now it would be like this information wasn't there, right? So they've given you a table, all right, and they've said we're not going to give you the CO2's enthalpy of formation. So what they do need to give you is the enthalpy, change in enthalpy for the system or for the reaction. Remember, either one of those symbols should work out. And so through our calculation, we already know that it's going to be negative 2,600 kilojoules. So to some extent, we're just like going to be back calculating and confirming the value that we already know should be there, even though I've just crossed it out. So with that, the work changes slightly, right? So this now becomes almost, we could put it as 4 times enthalpy of formation. That we sum for. We know that next would do is make the math a little bit of this negative equals away negative, right? Because I want to subtract this to both sides. So what essentially is going to happen, it's like I'm adding this information to the other side. So it's like plus 2 times quantity 2 times 227 plus 5 times 0 puts us at, we're at negative 2146. So now negative 2146 kilojoules is going to equal 2 times negative 286 plus 4 times change in enthalpy of formation for CO2. So with that being understood, right, I'm going to have essentially the result that, so minus negative or minus quantity 2 times negative 286, doing that. So we're at now negative 1574 kilojoules is equal to 4 times change in enthalpy of formation for CO2. And so, in essence, change in enthalpy of formation for CO2 is going to equal 1574 kilojoules divided by 4, which should equal, fingers crossed, divided by 4 should equal negative 393.5 kilojoules. So that's another version of the way that they can throw that problem at you. So I hope that this helps out, and good luck putting it to use for yourselves.